Okay, hello guys. Welcome to lecture 12. We're going to talk about ADT trees. ADT is abstract data type. So we are using data abstraction or like user-defined data type to create trees and use trees to store and access data. So the trees is covered partially in Computer Science 210 DVC. Yeah, I'm not sure they actually don't have ADT type, but they do have trees to talk about the tree data structure. So let's get started. So the study goal is what is a tree and what are the names of the components of a tree, how to create a tree with data abstraction, and why is this will be static, like which means you can modify it. And the fourth, how to use recursion, iteration, and or its comprehension to create a new tree based on the old tree. So let's get started. First one is tree. So this is a tree. The tree in English or natural, like in the nature, the tree is like you have a root, starting you have a root starting at the base point, and then you have a lot of branches, and each branches also have a lot of sub branches. So it will be more like that until you get to the end of the branch or the end of the stick, which is a leaf. So we usually have a root and branch and a leaf as a tree, like in the nature. Like as you observe the tree, you know about it. And so for computer science, tree is a data structure organize the data as a mind map, or maybe a tree. For example, in mind map, like this is our first lecture, I made the mind map there. So in the mind map, I have a root, and then I will have several branches, and each branches also have their sub branches. So for example, I have Python basis, and then I'll get data type is one of the branches. And the built-in data types for here is the sub-branches, is one of the sub-branches of the data type branch. And then I still have integer, string, that kind of stuff. And they can be treated as a leaf because there are no branches connected to them. They are the end of the branch of they are the ends of the branch of built-in data type. So in the computer, like we usually have kind of like arrangement of files. And for example, I have documents here. So document is kind of like a root uh, that stores so many stuff. And I have two branch. One is Adobe, one is GIS. And then Adobe, they have a branch, Photoshop, and then GIS also have two branches, is add-in and default GDB. Yeah, so um, this is the computer. Like when we use computer to find our files, and this can be one of the examples of how trees in our daily life is kind of like a data structure comprehensively. And this is my map, and this is a computer like file address. So this is another thing, like this is the trees we are going to talk about when we start coding. Usually trees, when you draw a tree, it will be like this. So the first one, um, like at the top, which everything starts from here. We call this a root. This is the root of the tree. And then the tree, we have knot. Knot is like when you have a root, and then you have branches. And the dot here that connects the main branch to sub branches is called knot. And knot is where I store the data. Is the container that store data and connects between the root and the branches. And then I also have leaf. Leaf is one of the knobs that do not have any sub branches below it. So this is called leaf. Like when you have a tree, the leaf is usually doesn't have anything else. It's just itself. And then label. Label is the data that we actually stored in the node. So label for this node is free. And we also have branch. Branch is like we have a root and branches that the stuff below the root, like all the stuff below the root containing sticks, containing a lot of knots and also leaves. Yeah. So this is the structure of a tree. We have a root, a knot, a, a label, a leaf, and branch. Yeah. So components of a tree. The root is the start of a tree, and which means it has no parent nodes. Like because everything starts from here, is the great grandfather of all the data. So parent node means that there are also some stuff above him, but we do not see any data above the root. So root is the start of the tree, which has no parent nodes. And node is the place where the data is stored. So we have one and two, they are data. And node is the place which stores this data. And label. Label is the contented data in each node, like the data we actually want to store. And also the leaf with no child nodes, like which means that there's nothing below it. Yeah, it's the end of the branch. And branch is the node and the subtrees connecting to the node. Like it just say like there are subtrees. Like you have a big tree and there are lots of subtrees and they consist of a big tree. And the subtrees is called branch. It's called branch. Okay. So this is example of tree. We're still using this example. And this is called the height of the tree. The height of the tree is that uh the depth. Like depth means for example, I start from 1 to 2, and the 2 is in depth 1 from the root. So 100 is also the depth from 1, like how many levels we have to travel until we hit 100. So this is the depth. And the height of the tree is the depth from the root to the youngest child or the youngest leaf. Like we only have like the youngest children of this tree is 100, 101, 102, 103, and 104. Yeah, like they are the youngest among all. Like which means they are uh, the very the very end of the tree. So the level traveling from 1 to 102, like one of the youngest children, is 2. So the height of the tree is 2. Suppose I add another, like add a children node at 102, say 105, and the youngest child of this tree is 105. So the height of the tree will increase to 5 because I will travel 3 levels to get to the youngest child. So the height 0 is 1, and then for 3 here, the height is the depth is 1, and then 2, and then 3. Yeah, this is height of the tree. And we have to talk about binary search tree. Binary tree means that for each node, like non-leaf node, they actually have 2 branches for each non-leaf node. So binary search tree is more specified as a kind of binary tree, which is um, for every non-leaf node, there are only 2 branches. This is the definition of the binary search tree. And uh, the labels from the leftmost to the rightmost are in ascending order. This is one kind of tree in binary tree, this group, and this is called binary search tree, which means for every node, the left node, the data stored in the left node will be smaller than the data stored in the right node. Yeah, so as you see, we can see it has ascending order. From the leftmost, we have 1, and then would be 2, 3, 4, 5, 6, 7, and yeah, they are in ascending order. So if I want to search a number, from the starting, let's say 3. I want to search 3. Which place is free the data free stored, and then I will compare it with the root first, and yeah, I say smaller than, so 3 must be left side of 4, like because we actually order the data in ascending order, so we can just compare that. If that's if the data is greater than the label, it will be on the right side of the node. Otherwise, it will be the left side of the node. So compare 4 and 3. So 3 will be the left side of 4. And then I will still compare. I will see 3 must be in this place, must be in the left side of 4. And then I'll still compare 3 to 2. I'll see, oh, 2 is less than 3. So that means 3 will be on the right side of the node that contain 2. So will be the left side of this. So and then we will find where 3 is stored. So this is binary search tree. Yeah, but we will not discuss that in this. Like we will talk more generally about the tree because this is how you develop a more general solution to all kinds of trees. And why I mentioned binary search tree is because it appears on Computer Science 210. So that's why. So, and then we talk about data abstraction tree definition. So we now use data abstraction to define a tree. So I actually had that from UCB, and this how they define a tree. I do a reference to this stuff, and let's see. We will just use this definition to create and access data, like store and access data on the tree. So we say for data abstraction, we usually have 2 tools to achieve data abstraction. One is constructor, another one is selector. So constructor, which means we use this function to create a new tree. Like we don't have to actually know about what is that in the tree function. We can just say, oh, what elements it will take in to create a tree. So tree, it will have the first place. It will have a label. Suppose I want to create a tree, maybe a leaf called 1, like store 1. So label here will be 1, and branches. It depends whether you are where you are to create a leaf or not. Like if you are to create a leaf, because leaf does not have any branches, so you can just leave it blank, or you can just insert into, like you can just take in an empty leaves. But you are to create a non-leaf node. The branches will be a list of some other subtrees. So actually, branches is a list of branch. Branches is a list of subtrees. So you will have to contain other tree stuff inside. Like I have 2 subtrees here. Maybe you can have more. This is you have to pass it into the tree so that you can create a new tree, use the subtrees and also the label. So suppose this is they are 2 leaves. Suppose this is leaf 2 and the tree 2 and tree 3, because they are leaves because I do not pass in any branches inside. So it does not have branches. So they are leaves. So this will return the tree in this type. So 1, 2, and 3. So 1 is the node, the parent node of 2 and 3. And 3, 2, and 3, they are leaves. So they do not have branches. They are connected to 1. So 2 and 3 are are the children nodes of the node one. So yeah, so this is how we create a tree. And selector is to return the data as we demand. Like suppose we want to have we want to know the label of a tree. Suppose this tree. When we say pass into this tree into the label function, and you will return the parent node of this tree. So this is one. So it will return one. This is label. And branches, like you will return branches of this tree. So it will be tree two and tree three. Tree three. It return trees, not labels. But for label, it will return the label. And its leaf function is to pass into a tree, and so that you can it return true or false, so that you can know that if the tree is a leaf, like usually just to check if they have branches or not. Um, suppose I put in the tree one, like tree one, two, three, and you return false because I actually have branches, although they're leaves. The each branch is a leaf, but they are branches. Yeah, so it will return false. But if I just input the tree two, it return true because there are no branches below the node two. So you will receive a true. If you take the tree two inside the isLeaf function. Okay, so we are going to use these four functions to create and to select data from a tree. Okay, so have a small summation. Define tree label branches equals empty list. Like this is default set. Like if you don't pass any values in this place, it will pass in the empty list as a default value. So it says text in the label of a node and its branches, so that it can create a new tree. If the node is a leaf, the branches is none. Yeah, because like there's nothing else below a leaf. And define label tree. Label of tree returns the label of the first node. Like return the label of the root, you can say, the label of the root. And define branches tree. You return a list of branches of a node because for a tree, branches is a list of the subtrees that create this tree. So you return a list of branches, and its leaf you return true or false to know about if the tree is a leaf. Okay, so do not break abstraction barrier. You just do not need to know how it's defined, but you must use existing tools to find out data and to build a new tree. So yeah, so you can only use four functions to achieve all your goals, and do not try to learn how they are constructed and try to use that on your own. You have to use existing tools. So the data stored in data abstraction function are static. They cannot be modified. So we must build up a new tree if we want to modify a tree. Like why is it static? That's because we do not have the tool to change the data. We do not have a tool to change the data of the user-defined data type. You can use OOP, which we'll discuss in the next lecture. You can use OOP to create an OOP tree, and OOP allows you to modify your data. But for data abstraction function, when you create all of the stuff, it is all set, and you can only access data. You cannot change the data because we don't have such tools to change the data, and we yeah, we don't have such tools to change the data, so that's why. And since they are static, if you want to change some data, you can create a new tree. So with your modified data and your also some other previous values to create a new tree. Yeah. So in other words, just to create a new tree if you want to modify a tree. This is important. This is an important concept when you deal with ADT tree. So I think that is actually even simpler than having an OOP tree, which can allow you to modify the data, because you just find out something that is to be modified and to create it, and then you just put all your old values in into that to create a new tree. That's actually I think it's easy. Yeah, it is easier than to modify an OOP tree. Yeah. So okay, so we now have to try on our own, like to do tree implementation, like how to code with trees. So the first thing, we have two example and then a practice. So first thing is to find out the keyword in the tree. If found true, if you found out the key word, you return true, or else you return false. So suppose I want to find, I have two example. Suppose I want to find 103 and want to find 105. One exists in the tree, one does not. Yeah, so maybe other not same. Like we have three examples. So suppose like we are to travel through the list, because we just want to receive true or false. Uh, so that we just want to have true or false, so that we don't have to construct a new tree. Just use the old tree. Yeah. So here's some small hints. You use any function to return the first true value in the list. So I can just like, because we have three subtrees, and then each subtree also have their own subtrees, also have their own branches. So if I travel through the branch, then it will return false. Do I just return false if I only travel this in this path? We do not want to only have the false, because the data may be stored in other paths. So which means we use any, like, which means if I found out maybe so many examples, we have so many paths. If we find out any true, which means we actually found that, we just want this true value. We just want this true. So so that which shows that we found out. So which is more reasonable. Like if we find out the first false and then you say conclusion as false, it does not make sense, because maybe the data exists in other paths. But on the other hand, if you have all of them false, which means you cannot find them, which means any function will still return function will return false, which shows actually we actually didn't find them, which also makes sense. So we use any function to collect all the data, collect all the conclusions uh, as we travel through a path. So after collecting all the conclusions, after we finish all the paths, we will start evaluating it, like to see if we actually have a true value, have a true. If so, return true, else return false. Yeah. So use label and is left to selector. So to travel this 103, 4, and 105. So we will use recursion. See, yeah, we will use recursion. Every time you have to like compare the value with the label of the tree, which is label tree, like compare the root. If it's not, you will jump to other branches. So you have a for loop saying that for each branch in the branches of this tree, and then you will try evaluating it. Like if you hit the value, wait, yeah, if you say like the label is equal to the value we want to find out, you just return true. After return true, like because since I found that, like we don't have to travel that again, continue our traveling, because we found out true. This is all what we want. So if you say, oh, it's true, return true. Or else, to check if this is a leaf, like since I have this is false and this is true. If this is true, it will be the leaf will be treated as other nodes, why same as non-leaf node. If it's true, we don't actually, it does not matter whether it's a leaf or not. Yeah, but if I travel to the leaf and it also says it does not match, so we will return false. Why? Because that's the end of this path, and we that is the end of this path, and we cannot travel the stuff below because there's nothing below. So you return false, and then you will collect all these conclusions and to try to find out a true among all falses. So this is how we have to implement the tree. So we will have two base cases. One is that we find out the value, so it does match. It does match, so we return true. No matter whether it's a tree, whether it's a leaf or it's a long leaf node, it does not matter. But otherwise, if you travel through a path and then you've been to the end of the path, which is a leaf, and it also does not match, so you return false. So because we cannot find the value in this path, yeah. So it finished, and I will travel through the next path. Yeah. So we have these two base cases, and the next one is if neither of these apply to me, which shows I'm in the middle of a path, maybe somewhere between 1 and 100 or 101. So I would just have a for loop, like jump into the branches and start exploring that. As if you are in a new tree. Start exploring on the subtree, and then you collect all the stuff, and then you will try to find out whether you have a true in a lot of forces. Yeah. So this is the answer. Say find out we have the tree. I say T here and keyword. If label of T equals to keyword, you say label of T equals a keyword, you say return true. This is, and also else if is true, return false. So this is two base cases I mentioned, like the label of T. I don't care if that is a leaf or is not a leaf, but it matches, so I will return true. And otherwise, like for this otherwise, that actually includes whether like when the tree is a leaf. Otherwise, I will evaluate, oh, this is a leaf, and actually reach the end of the path, so I'll return false. I still couldn't find that in the leaf, so I will return false. And for else, I'll return the any function. For any, I pass in a list. A list is to find out like according to recursive leap of faith, we have to show that find out branch keyword actually returns true field value, true or false, like which is the conclusion after we travel through a path and check if I actually find out the keyword, and we have to use this comprehension to try to construct all of these true false into a list, all these true false conclusions, like for branching the branches. So after, like for example, after traveling the route, I have 2, 3, 4, and there are branches. I will try to travel through all these branches one by one, and then to collect this true or false. So for a branch in the branches, so you can treat a branch as a new tree, but it's just a part of tree in this big tree. Yeah. And for this branch, I would also take in the function, and the function will try finding if that's true or false. And we have to believe it returns correct result. So we will have maybe either true or false. And then after looping through all these branches, I construct these results into a list. And then I use an any function. I use an any function to find out if there's a true. If there's a true, I'll return true. Otherwise, I return false. Yeah. So as I say, like for 103 here, actually, I will for the base for the bottom of the recursion for the base case, I will have this is true, so I will just return true. And also for 4, and for 105, suppose I'm traveling for here is 104, and if label T is keyword, return true. Simply like this is label T is not keyword, so it does not return true. So I will jump to the next base case. So it is a live. So I return false since I know it's not keyword. It's not it does not match with the keyword, so I will just return false when I hit this live. And also for other results, I also got 5 falses. And for the last one, I also got false. So for any function, I will return a false. Yeah. So this is the first question. And for the second one, I want to convert all the even numbers to be 0. Suppose I still have this tree. So we have to find out all even numbers. Suppose I have 2, 4, 100, 102, 104. I want to convert that all into 0. So let's try. Yeah, it will be like this. So how? We have to use a tree function to create a new tree because we actually modify data in the tree. So we can only use tree function to create a new tree. And then this is the stuff we have to take in. So we will try to try how to implement this. Okay, so suppose I will still have label and I will still have isLive. So for label, we have to check if label of a tree is even. How we check even? We mark by 2 to check if it's even. And if it's even, like I will construct a new tree. And then this will be 0. Yeah, this will be 0 because I actually want to convert them all to be 0. So I will abandon the old values. For this one, this is the subtree. So this will pass in a subtree. And how we get a subtree? By using recursion, actually. By using recursion, it implements the trees, and I put in here. So then you construct a new subtree with the not 0 at the bottom, at the top, and other trees that are actually well implemented at the bottom. So this is suppose this is even. How about it's odd? So I'll have tree. Still, the new subtree is created by recursion. And how about this? This will still be the old value. So I will still have label of t. Yeah, still have label of t to pass in, like as if it does not change at all. So for the isLive function, this will be simpler, like because we do not have subtrees. So we have tree. Oh, yeah, we actually still have to check if it's even. So if it's even, tree not will be the tree will be the leaf 0, and otherwise still be the tree label and label t as if it does not change. So because it's a leaf, we do not have branches because the second place we have branches. So yeah. So the base case is like we have to check label of t. Have to check label of t. I think we have to check if that is a leaf first. If that's a leaf, and we'll check if that's odd or even. Yeah, and then you will return the leaves. And otherwise, which shows this is a non-leaf node. You will have to return this things instead. Yeah, like shift if it's even and shift not, and then along with the subtrees, and you will use recursion here. You will use recursion. So this is the answer. Yeah. So yeah, we have to check if the first one is leaf is actually the base case. Yeah. And the first one is if it's a leaf is true. So label of T Mark 2 it satisfies two conditions. One is this is a leaf, another one is this is even. So I return G of not, G is 0. Yeah. And otherwise, satisfied with either one, which is this is a leaf, but this is not an odd number. So you return tree of label as if it does it as if it is the old one, like because we don't change that. So we still passing label of t into tree. Yeah. And else if label of t in mark 2 is equal to 0. Like for here, this is this is not a leaf, but this is an even number. So you pass in the label saying is 0, and then you use recursion here. Like you use recursion, but recursion only returns one of the branches, one of the branches below this label. So in order to make them a list of the branches, you use list comprehension. So for branches of T, uh, say this is say we use this one. So for branches of T, we actually have this branch and this branch. Convert even only returns either one of this. So we've used this comprehension because branches is branch 1 plus branch 2, etc. is a list of subtrees. So you use list comprehension to collect all the modified branches. So convert even. So for I can be either this 100 or this 101 path, two paths. And then for either one of these, you will still put into the recursion function and to assume that returns a true result. And then you put it into the list to say, oh, this is the branches, a list of the trees, subtrees below 2. So you use recursion to find out either one of these, and you use this comprehension to collect all of them together. Yeah. And for the last one, it fills into neither of the conditions that the tree, like this is not a leaf, and this is also not an even number. So you will return tree of label, same as usual, but also you will be the same as you type in you say in the label tree mark 2 for this, because for this label, this will be the old value, but it doesn't mean the subtrees below you will be as same as before, because maybe some of the nodes contain even number and we still have to modify them. Like suppose for 3 here, like the value, we can keep this as the old value 3, but it doesn't mean the stuff below it can also not to be modified. This is 102. This is even number, so we still have to modify that. Yeah, so we still have to put the branch one by one into the recursion function, and then returns a well implemented tree to us. So this is how we say convert even function. Yeah, and then we have a practice. Practice is to return a list of paths with every path also a list length less or equal to the input height. So I have a tree here. So I actually want to find how many paths so that I can actually travel 2 levels in the tree. Yeah, I would say equal to the input depth. Yeah, height tree is this height tree is actually 1, 2, 3. The height is 3, but depth is smaller or equal to height. That's the there will be only one height in the tree, but there can be several depths in the height. Height can, yeah. This is the domain of the depth. Yeah, it can be as small as 0. It can be as big as a height, the height of the tree. So yeah. So okay. So suppose for this example, suppose I have a tree and I taking the depth 2. I want to find all the paths that I can spend less or equal than 2 depths to travel through. So suppose I start with 1, and I want to check depth equals 2. Right, this is the one I put input into. So I will have 2 here. So for 2, I have 2 options. One is 3, and I finish traveling 2 depths, and also 4, still finish traveling. And next one, I will check depth equals to 1. So this will be only 4. Yeah, this will be only 4. Mhm. So this is how. Okay, so we start implement this. Mm, I think, yeah, copy of this. So we start thinking about it. Uh, oh, so so for if and else if, it must be the base case. So we can start from the base case. So find path t height. As we see, we will keep track of the height though. We will keep track of the height. Um, let's say uh, um, we can try and analyze it. So we have if and else, it will be the base cases. And also from the else part, what would that be? For else, for paths is in the list, and for something in something, and then you return paths. So paths is a list, and we want a list of paths. So this is the list. Now it's empty, and we have to refill it with the paths. Yeah. So every path is also a list. So the list is we have to include all the labels and construct them into a list, and then put this list into the list path again. So it will be list of lists. Oh, so uh yeah, so we will think about uh start from the base case. Uh, you say uh okay, so we actually have 2 base cases. One is to check if I reach the height 2. Another one is, remember we have a 1 footpath. Why we will stop here? Because 4 is actually a lift. So if we travel for a lift and there's nothing below, we will stop and return this path as well. So okay, so this makes more clear. So I would say if height uh, is equal to 0 or maybe less than to make it safe. To return something, and also else if its live is of live of t is true. Oh, uh, return this. Okay. So what things we have to return? Uh, so that would not be that would not be recursive call though. So I would check for the stuff below here. For something in something. Uh, I think that would be branches. Uh, yeah, I think that would be branches. Uh, you can try. Actually, branches T. And this one, I guess it will also be recursive call and this comprehension. But the thing is, we have to figure out what stuff we have to return in the base case so that we can think about what will be returned in the recursive call. So, uh, hi. Uh, so, uh, maybe we'll return the label of the T, label of the tree, but we'll put into this. Yeah. Also send stuff. Yeah. For branching branches, um, I would say you can extend something into the path. So you can either use a path dot extend, or maybe use the stuff which we say it is plus equal. Yeah, will be the same. For this one, it would be a list comprehension. Yeah. So for every time, so suppose I have a branch is 1, 2, and here's also a 3. Um, let's say, mm, uh, wait, why don't we, um, because it's a list of lists, and then like because we have to keep track of the first one and the second one, like we have 1 and 2, and this and 3 and 4 are distinct. So why don't we just increment like actually for every loop, it will extend. It will extend. Yeah. Okay. So you extend this, and this will be list comprehension and also the recursion call. Uh, so I would say, suppose for looping here for the first time, I will have 1. Yeah, I will have 1, and I will also have the stuff 1. And then next one, I will implement like 1, 2, and 1, 2, 1, 4. And the next step, I will have 1, 2, 3, 1, 2, 4, 1, 4. I'll be like this. Is this reasonable? Yeah, I think, yeah. Um, so every time I will append kind of, maybe this one, I guess. I guess instead of using, I'll use list of lists instead. So mm, extend. So I would say the first one will be label, kind of label T, and plus, yeah. Oh, this will be list extend. Maybe use this one. No. Um, so wait. So I'll be having the label first. Like I input that. Uh, maybe I would say I would say pen. Say pen. And this one, 2, 2, 4. This one will be recursion. Uh, because it return a list of lists. So I'll say for branch. Yeah, I should say actually it will be kind of like this. So we'll find a list of lists there. We still have, yeah. Uh, okay, okay. So I actually looked up the answer, but it's okay. I think I understand this. So for the base case, high is this return list of label T, and also its live. But how we implement this part is important. Like, so suppose we start from the bottom, like we actually look through the list. So suppose we actually look through the list until the 3 and 4. until 3 and 4. And then you say, um, I will I will return label 3 and 4, right? And then I will this will be returned to here for find path. And since I have 3 and 4, I actually have two paths, and then I will want to append two at the front of them, at the front of both 3 and 4. So then, since I is since I this here can be I can be 3 and also 4, and it's actually in the list. Wait, I think, yeah, for branches can be 3 or 4. I'll start from here. Like for next step, I want to extend label 2 at the front. So I will say 2 plus 3 or 2 plus 4. That it will become 2, 3 and also 2, 4. So I will return since paths extend 2, 2 and 3 and 2 and 4. So this will become 2 and 3, and this will become uh, 2 and 4. So I actually make them into the path. Yeah, actually make them into the path, the list of the paths. So you have 2, 3 and 2, 4. And then I will return this again back to here. So this one I will have 1. This one I will have the label 1. So I will append 1 into 2, 3 and also 2, 4. But this is only one branch of 1. And I also have another branch which is actually 4. So I would say, um, so for this branch, which actually has 2 elements, this will be this, and then I will also label and to append 1 into 2 and 3. So and then I will just extend to the path again. So this will be 1, 2, and 3, and this will be 1, 2, and 4. So this is the path. The new path leads in the situation when we are back to 1. Yeah. So and then you still have 4. 4 is another branch, which only contains 1 element. And then you still have used label 1 and then input 4 together. 1, 4. Yeah. So this is how. So if high is less or equal to 0, return this list of label t. On else if we return list of label t. Is list containing a path. So this is the raw path, starting from the bottom, starting from 3 and 4, and also this 4. Yeah. And then you have the base case. We have 2 situations. One is that the height will be less or equal to 0. Another one is you reach to the leaf, one of the leaves. And we return list of lists. And finally, you use recursion recursive call to return a list of lists. So this is extend, path extend. So for each one label of T, it will be, suppose I have 3 and 4, I will return to 2 here. So the label T will be 2. So label T will be 2 and then I have 2 branches. One is 3 and one is 4. Each has 1 element in the list. And then I will use because it construct to be list of list of 3. So it'll be list 3. So it will be list 3 for one branch and list 4 for another branch. And then I will append 2. I will put a 2 at the front of this 2 lists so that I will have 2 and 3. So this is for the branch for the branches of 2. And then I will put this 2 together into a list, and then we create the path. Paths when into two into a new path when at the branch 2 correspond to 1. When parent is 1, this is the leaves of branch 2. I actually have 2, 3, and 2, 4 here. Yeah, because when I'm dealing with when 2 is parent and I have 2 subtree is 3 and 4, and then I append the label 2 at the front of each of them, so that and I'll append into path. I will put them into the paths, and then when I'm okay with branch 2, I will back to 1. But for 1, I have 2 branches. One is 2. Another one is 4. So for 2, I have this. So I have this list 2, 3, and 2, 4. So for I in find paths, suppose because for here for when parent is 1, I will have 2 and 4. So for the branch which parent friend which at the root of the branch is 2. So I will have 2 elements, 2, 3, and 2, 4. And then I will append, because for here label is 1. I will put 1 into the front of both of them. Yeah. So I will have 1, 2, 3, and 1, 2, 4. And then for 4, it runs under base case. It runs from base case. I only have 1, 4. So I'm okay with 2, which root is 2, and I will have the root 4. For the root 4, I only have this, and we only have 1 element. And then I will make 1 to be the front of this. Okay, so we are actually succeeding in dealing with 2 branches. So it's 1, 2, 3, and it's 1, 2, 4. And for this one is just 1, 4. So they are all paths. So I want to make them into a new path. I want to put them all together to become a list. So for the path here, don't be confused. It's under the branch where the root is 2. For when the root is 1, it will be up to the another frame. So the paths will be another variable. So the path it will become 1, 2, 3, and 1, 2, 4 plus 1, 4. You put in you put them together. So this is a list of path, and it's also a list of lists. The inner list is a path. The outer list is a list of path. But the list of path only contains 1 element, only contains 1 path. So we have 1 list of path together. One list of path contains only 1 element, and list of path contains 2 elements, and we add it together. The list of path containing 3 elements, and which will be the result of this one. So yeah, so eventually we figure that out. We start from the raw case, and then we add the root. We add the root label by 1 time together, and to figure out which branch has a path, and another branch has also list of path. And then for one, we modify the path first, and then we put them all together. So they will return the list of path. Okay, so this is the end of the lecture. And yeah, thanks for watching it. Yeah, we'll see you next week.